Good day. In this video we're going to talk about nuclear stability and radioactivity. Radioactivity. If you remember when we talked about fusion in the last video, I said that if for instance you take two protons and make them be very close, they will fusion into helium, to one proton, another proton, to hydrogen. It's going to become helium, a version of it. In reality, you have four. You're going to need four of them to become helium. It's going to be four protons. Anyway, so if you fuse four protons, you're going to have helium, and they're going to live happily in the nucleus. However, there is a huge repulsive force given by Coulomb law. This is the constant, 9 times 10 to the 9. Coulomb constant, right? Newton meter squared, Coulomb squared. But then the radius of a nucleus is of about 1 times 10 to the 14 meters. Put that number here in the r square. The charge of the electron, the charge of the proton, the constant, and you're going to get humongous forces. Meaning the two protons feel a very large repulsive force. It is actually extremely hard to make these two merge and fuse. So if it's that hard to put them together, what keeps them in the nucleus? The protons live happily together, even if there is an extremely strong repulsive force, the electric force. So there must be another force keeping them counseling the electric force. And that force is so strong that it receives the name of strong force. Right. The strong force acts as a super glue. It's a short range force. It affects protons and neutrons. Right? So basically they have to be touching, the two protons, whatever that means. The neutrons help, right? So the helium is very stable, right? The strong force does work at short distances and counteracts the electric force that is our long range force. Look at the R. The electric force becomes zero at infinity, right? Whereas the strong force only acts when the distances are extremely small. Now, what happens as you keep going in the periodic table to the right and down? You start getting atoms with more and more protons. Helium is very stable. There's a lot of strong force together in the neutrons and protons to overcome the electric repulsion. But as the nuclei become bigger, take for instance uranium 92, 238 or 236, doesn't matter. So I should put 236 little signs here, either neutrons or protons, which of course I'm not going to do, but I'm putting a lot. As you can see, what happens is, because it's 92 protons, this proton here feels a repulsion of the other 91 protons. Remember, the electric force is long range, whereas the strong force is short range. So at the same time, this proton is feeling the repulsion of 91 other protons. Is feeling the strong force of the neighboring neutrons and protons. So at one point, what happens is that the electric force wins and the system becomes unstable, right? And the electric force win and break the nucleus apart. That we call radioactivity. It's impossible to know, once you know an atom is unstable, once you know an atom is radioactive, well, you know it's going to decay. right? It's nuclear decay. We know it's going to decay. We don't know when, right? But it's well. As a general rule, after 82 protons, all atoms, all nuclei, all isotopes are radioactive. You can have some radioactivity also depending on the specific isotope. For instance, if you don't have enough neutrons to help, the isotope will be radioactive. Let me show you a graph. This graph represents the stability, the stable isotopes. You have number of neutrons, number of protons, 1-to-1 ratio. Look how the stable nuclei tend to go closer to the 1.5-to-1 proton-neutron ratio. Right? That happens because the neutrons help with a strong force, but they do not contribute with the electric repulsion. And as you can see, after 82, no more. Let's bring this graph to the other table. You see, those are the only nuclei that are stable. Okay, there's another graph. So I'm putting both here. This is the original one I showed you before, and this one shows you not only the stable nuclei, but also all the unstable ones. And it gives you the type of decay, of nuclear decay that could happen. We mentioned one type, which is this one, the alpha decay, before when I talked about the uranium, in which part of the chunk, one of the chunks that flies away, it's an alpha particle, which is a helium particle, ionized, meaning nitrogen, neutron, proton, right? So it's a helium with ionized, no electrons. Well, that's the alpha. These are electrons and anti-electrons, and we will talk about them in another occasion. Now, once an atom is unstable, you know it's radioactive. People started to study this phenomenon after a guy called Becquerel. Becquerel found that some uranium rock exposed photographic film that was sealed in an envelope. So light could not go through the envelope, but whatever this rock uranium was giving exposed them. So there was an interest after Pierre and Marie Curie studied this stuff, and they discover some aspects that I will discuss with you right now. So we know we have a sample of a material that is radioactive. It has an N number of, this is the number of undecayed nuclei. And what they found was that the decay rate, or the activity, the decay rate at which the isotopes transform was proportional to the number of isotopes, of nuclei. This is the definition of a first rate reaction, just as you covered this in chemistry of solutions. So it's a differential equation. Lambda is the decay rate. In chemistry they call it K. Here we call it lambda, same thing. And you can solve the differential equation by doing this. After a little bit of calculus, you get this solution. The number of undecayed atoms is equal to the initial one times an exponential minus lambda t. If you plot this, you're going to get an exponential that goes to 0 at infinity, of course. Right? Here is your initial number, and it's an exponential minus lambda t. Just like in chemistry, we define the activity as the absolute value of this ratio, this rate, which gives you ln, lambda n, but n we said is that, so we can write it as lambda n 0. And finally, we cut this, we call this the initial activity. And what this gives you is this sausage of an equation, right? You can use this with this, or this with that, or this with that, or this too. It doesn't matter. Everything is equal to everything. Depends on, it was going to depend on what they're giving you. I'm also, from chemistry, I'm going to remind you that the half-life is the time needed for half your sample to decay, right? So that means, using this equation, when the time is a half-life, the actual number is the initial over 2. So n0 cancels. You get that 1/2 is lambda t 1/2. You take the logarithm on both ends, and then you get that the logarithm of 1/2 is minus lambda t 1/2, or that the logarithm of 2 over lambda is the half-life. This is the definition. So if we go here on the graph, come on, green, right? That means that if this is the initial time, well, when this goes to 0 to half, this is 1/2 life, right? Because this is a linear, this is a first order to go to 4, 1 and 0 over 4. This is 2 half-lives. To go to n 0 over 8, that will be 3 half-lives, right? 3 half-lives, which allows us to write this. N is n0 to the n, where n is the number of half-lives that have lapsed. You see, 1/2, 1/4, 1/8. You see, after, let's say, after 3 half-lives, you get, so the 3, which is 1/8 of n0, which is what I wrote here, right? This is an 8. And that's all the math we need. Now, units for activity, as you can see, is n over t. Nuclei is actually decay per second. Those are the units for activity. 1 decay per second is also a becquerel. And because we get usually a lot of decays in a second, 3.7 times 10 to the 10 becquerels is called 1 Curie, in honor to Marie and Pierre Curie. We'll do problems in class involving this material.